right. So basically, your book says the reason we're interested in interstellar medium is it's the place where stars are born. And on the flip side of that, there's a lot of gas and dust that ends up getting released at the end of stars' lives as well. And so we're going to look at how that all takes place. So in this image, you see that Barnard 86 that we were talking about before that was in the book, the dark nebula, and then the book also shows it in infrared so that you can kind of see the stars behind it that are obscured when you're looking in the visible. And so this is probably somewhere where, maybe within this cloud, greater cloud, there's some kind of star formation taking place or about to take place. So how does that actually happen? We've done computer simulations to try and simulate this, but also looking around and seeing evidence of different stages of this helps as well. But in a nutshell, what we've been able to deduce is that generally speaking, you're starting out, if you have a large enough cloud of gas and dust, it's got to have many, many particles to it. Then sometimes at some point what can happen is that it becomes unbalanced. So during a normal period of time for this cloud of gas and dust, it's sort of stable in the sense that it's not dissipating, but it's also not contracting and becoming more dense. It's just this diffuse thing that's out there. So you can liken this a little bit to, again, take it with a grain of salt, but clouds that you might see in the sky, you might see a stable cloud for a while, and then maybe something happens to cause the cloud to break up or dissipate. And so sometimes what can happen is the gravitational influence of some nearby event, perhaps a star passing by or a supernova going off, can make this a little bit less stable. And once you tip the scale, it's always this war between outward pressure and the inward pull of gravity. Because remember, the universal law of gravity basically says that everything that's massive is going to attract to one another, right? It's not like electricity where like attracts and unlike repels, because we don't really have a situation here where we're talking about anti-matter. You just have matter, and so mass is mass, and so it's all going to attract. And so gravity wants to kind of bring everything together, but outward pressure wants to push everything apart. And once you tip the scale in favor of gravity, by whatever means, maybe again a star passing nearby or a supernova going off to somehow influence the motion within this cloud, then what can happen is that it can start to condense. And as it's condensing, it's not going to condense uniformly, so different pieces of it will become maybe more dense than others, and what will happen is then fragmentation will occur. So rather than this whole thing becoming one dense thing, maybe you get a clump over here, and 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 so it fragments into several pieces. But each one of these pieces now is denser than the cloud from which it came, okay? And then that process might continue as gravity is starting to win this war and pulling things closer together. Then the closer they are together, the more that the gravity can influence it even further and attract those particles to one another even more strongly. And then within each one of these clouds, maybe you have sort of a similar thing taking place where maybe this clump gets a little denser than over here, and this clump, and then you get a clump over here, and so each one of these then maybe clumps off to form subclumps, again, each of which are denser than the cloud from which they came. And so what you have here in this schematic over on the right side, excuse me, each one of these little clumps is about the size of our solar system. So from here, you can have maybe a star form out of each one of them, perhaps. So basically, when you have star formation taking place, it rarely takes place in isolation, and I think I might have mentioned that at some point in the past. essentially you're going to have what we sometimes refer to as a stellar nursery, where a lot of stars are actually being formed around the same time through the same huge initial parent cloud. Okay, and so once you get an individual fragment, then here's a timeline of what occurs from that point on to that fragment that itself will eventually become a star. Basically, you've got something that's starting to warm up and glow as it's contracting and collapsing, and once it reaches about 10,000 Kelvin, then you'll see this kind of glowing effect occurring. And then it's going to contract even more, and this gas will sort of flatten out to a pancake shape, and the center part of it is going to be the densest, hottest part, which we're going to now call a protostar. Okay, and so, you know, you're talking less than 1 billion years or so, you've got a protostar in the center here. Now you see that there's kind of like these jets coming out of the top and bottom of it, and so what's happening there is it's really unstable, and so it's got some winds to it that will eject some material. So I always like to draw the analogy to a child that's really hungry and they're just gobbling up all this food, but they're like also spilling it everywhere in the process. So, you know, the inner part is gobbling up all the matter around it, but it's also spewing some of the matter off to the sides as well while it does so. And then, you know, after 10 to the 7 years, now you're going to have fusion, high enough temperatures here in the center for fusion to take place and for it to actually become a true star with its core fusing hydrogen into helium. Okay, so we can go back to this concept of the HR diagram, again, the Hertzsprung-Russell diagram that we talked about at length before the test, and we can track where things are in terms of the Hertzsprung-Russell diagram as the star is forming. When the star first is able to be plotted on the HR diagram, basically that just means it's got a high enough luminosity and, you know, a high enough temperature that I can place it somewhere on the HR diagram. And so when it starts to enter the HR diagram, you notice it enters kind of much higher than where it's going to end up on the main sequence once it's a star. And that's because it's luminous. Its luminosity is so great because it's so large in extent, right? It's still not as dense as it will be, so it's taking up a large diameter, and all of that is glowing. So you've got a very large luminosity, a very large radius. However, at the same time, its temperature is not that great, okay? It's still in the process of contracting. And so you've got kind of a protostar entering the HR diagram here. What's happening essentially is that it's converting this gravitational energy into light energy, right? As its gravity is winning, what's given off then is this light that's causing the protostar to glow. So it's a conversion of energy. You can think of it that way, gravity being converted to heat and light. Okay? Once the protostar keeps contracting, its luminosity will actually decrease, and that's just because its radius is shrinking. As it's contracting, its radius is shrinking. Okay, so it's giving off less light. Okay, but it's also moving to the left, so it's becoming hotter because its core is warming up more and more to the point where maybe fusion can start taking place soon, and so. More of that gravitational energy conversion then is now going to heat than it is to light. Okay, so either way, you know, when you're coming here, it's converting gravity into mostly light. Then as you go further, it's starting to convert gravity into heat as well. So the overall picture is that as the star is forming, it's converting the gravity into both light and heat. Until you finally reach a point where it enters what we would call the main sequence, and now its temperature is hot enough in the core that we can have fusion reaction taking place, and so it's considered to be no longer a protostar but an actual star. and it's on the main sequence now. Okay, so in its core, you're talking millions of degrees. In its surface now, if it's a star like the sun, you're talking 5,800 Kelvin-ish, radius of the sun. And inside, now we're no longer converting gravity to heat and light. Now our energy source is really just fusion. Okay, when a star enters the main sequence, there's an acronym that astronomers sometimes use, which is Zero Age Main Sequence, ZAMS, Z-A-M-S, Zero Age Main Sequence. And that just basically means it's finally reached the main sequence. We're going to start the clock ticking now. This is, zero age for its main sequence lifetime. And so when it's on the main sequence, then it's expected to live, if it's a star like the sun, for about 10 billion years. So once it reaches this point, it's fairly stable. It may fluctuate a little in its early stages, and as we'll see later on, it's going to fluctuate within the main sequence, but it'll stay within the bounds of the main sequence for about 10 billion years once it reaches that point of fusion reactions taking place. Okay. And so here are some observations. Again, this is a Trifid Nebula where you've got star formation taking place. The emission that you see here is from the formation of these stars nearby. The new star is basically heating up this nebula and causing it to glow. But then you also see these dark nebula also. And there's a dark nebula here that we can't really see, and maybe here, and even a reflection nebula. So again, this goes back to that idea that all the nebula, different nebula, are a lot of times taking place in the same region. And so this whole region might have initially been one of those giant clouds like what we saw in the left-hand side of this schematic. Okay, and then as it fragmented off, you've got a fragment here, you've got a fragment here, another fragment, okay, and even a star that's forming here at the center. Okay, this is a little difficult to read, but when you take a look at this on your own, you can maybe get all the captions a little bit more. But in a nutshell, this is basically how a star might form. And so you've got that initial cloud fragment. It's heating up. It's a protostar giving off a lot of strong winds. Okay, and then eventually the winds and jets fade, and you can get to a point where the fusion reactions are taking place. And this only takes millions of years to get to this point where now you've got a star in its truest sense in the center, and this gas and dust surrounding it is where planets might form. Okay, so out of whatever's left here, that might clump together in sort of a microcosm of what just happened, and you might get planets that form in orbit around the star. Obviously, that's what happened to our own solar system and other solar systems that we've discovered. We know of about 5,000 or so extrasolar planets in our stellar neighborhood. And we've even seen, there's an example called Beta Pictoris, where we have a stage that is still surrounded by dusty lanes. It's a new star, very young star, still surrounded by dust. And we even see like a lane of dust being cleared out that we think indicates that there's a planet there. So this is basically how planets form, which is kind of a side note since we're not talking about that. But getting back to the point where they're very young stars, they're sometimes called T-Tauri stars because they're a little bit unstable, and their luminosity is going to fluctuate a little until they stabilize. Okay, here's some Hubble images of T-Tauri stars. So they're, again, not quite on the main sequence quite yet. They're just above the main sequence. You can also think of that as the pre-main sequence because they're not yet born. But they are able to be plotted on the HR diagram. Question?
On the last slide,
yeah.
Like the whole process, you said that takes like millions of years?
Yeah.
Okay.
Yeah, a few million years. I think I misspoke earlier. I might have said 1 billion years here. but that's actually 10 to the 7, so it's like a million. 10 million or something. So a few million years is when you're going to get to this point. And that seems like a lot in our lifetimes, but if you think about the fact that the star is then going to live for 10 billion years, it's actually a really small amount of time for a star. So this takes place relatively rapidly in terms of astronomical phenomenon. Okay, and again here we've got some T-Tauri stars that are still having the jets. You can kind of see them here. And they're really still surrounded by the gas and dust that they formed out of. And so they're giving you a scale here that across here is 1,000 AU. So this one is the most zoomed in. This is just 1,000 AU, this tiny little thing. That's 1,000 AU. This is 1,000 AU. So still, this is like much greater in extent than our solar system. But you can kind of zoom in and see the different levels, and here you can see the jets pretty clearly. Back to the Trifid Nebula again, we think there's star formation taking place within the Stark Cloud. It seems like there's some evidence of that. Here's again a Hubble Space Telescope image of it. HST, that's what that stands for, Hubble Space Telescope. So anytime you see that on images, you'll know what that's talking about. And yeah, so this one is actually in the Orion Nebula, which your book discusses and mentions that it is one of the closer star formation regions. So we can look at it in a little bit greater detail. Sometimes these protoplanetary disks, if you will. So remember, it started out as more of a cloud, and then it turned into a disk, right? And so these protoplanetary disks sometimes are shortened in terminology to proplyds. But the Orion Nebula has a lot of that star formation taking place, stars being surrounded still by their protoplanetary disks and the gas surrounding them in the Orion Nebula. And so, do I have a picture of Orion? No, I don't. Orion is the hunter. There's a picture in your book, but it's basically, I always tell people to look for something that looks sort of like a rectangle. It's not a perfect rectangle, and then it's got like a belt of like 3 stars in the middle. Have you seen that in the night sky? It's one of the more easily recognizable constellations. But anyway, the Orion Nebula is like taking place like right around here in that region, just below the 3 stars of the belt. Okay, and so here are what we think are some protostars forming. Here's the light that you see coming from the protostar in the Orion Nebula. And so here's another clicker question for you. Anyone else want to change their mind? Because a couple people changed their mind. Are we good? All right. Okay, so, everybody's split again. Let's take a look. So the protostars, for protostar, its energy is coming from this gravitational conversion of, gravitational energy into heat and light. So the correct answer should have been C. A is once you have become a star, really. You're no longer a protostar. The dust nearby is not really going to provide a protostar with its own energy. And while the jets and the jets of the T Tauri stars are giving off energy, it's not really the main source of where they get their energy. The PP chain is sort of just related to the first one, that, again, that's once you're a star rather than just a protostar. Okay, everybody understand that now? Okay. Okay, so this is just a note in case you were getting confused at all. When you're looking at the HR diagram and you're looking at that main sequence, the stars don't actually move up along the main sequence. Wherever they land, they kind of just stay there throughout their lifetimes. It's just that, you know, when they're pre-main sequence lifetimes, we can plot them kind of above and to the right of the main sequence. But then once they're on the main sequence, they just basically stay within that region for most of their lives. They might evolve a little bit, but they're not going to go up or down on the main sequence. So how they change a little bit and where they go after that involves the end of the story of these lives. So we just looked at how the stars are born, and then I say, okay, once they're on the main sequence, they're going to stay there for about 10 billion years, give or take. And that's kind of a boring time where nothing is really happening other than you're converting hydrogen into helium, and you're basically in an equilibrium situation between gravity trying to push in and the radiation trying to push out. And so moving on beyond that, we can look at the end of the star's lifetime. So if it's a star like the sun, we call it low mass. Low mass, basically, I don't know, it's a little bit of a confusing terminology because it makes it sound exceptional, but really low mass is most of the stars in the universe are what we would call low mass. So low mass really just means low and average mass, I would say. It's only the high mass stars that are going to be different. They're the ones that are sort of exceptional. So a star like the sun, or any star like it, low mass is the terminology, but a star like the sun is going to keep fusing its hydrogen into helium, again, for about 10 billion years. As it's doing so, it may have started out with a fraction of hydrogen where, you know, it's maybe, you know, close to 90% hydrogen and just a little bit of helium. But as it's fusing that hydrogen into helium, more and more helium is going to be in the star. And if this is the distance from the center of the star on the x-axis, then that amount of helium that is increasing is not going to increase throughout the star. It's only going to increase near the core where the fusion reaction is actually taking place, right? So, you know, out here it's not fusing anything. Only in here is where it's fusing things. And here is where that hydrogen is being converted into helium. So this ratio is going to change as we're looking into the core of the star. You're going to see more and more helium as you go through the star's lifetime. Okay? And eventually that will spill out into the outer parts of the star, but, you know, it's going to take place first in the core. And so this is maybe where the sun is now, after about 4.5, it's not quite where we're now, 4.5, 5 billion years. Our core looks more like this than it did when the sun was born. And then at the end of its lifetime, it's going to be mostly helium in the core and just this tiny little bit of hydrogen at the bottom here towards the end of its lifetime. And once it starts to run out of hydrogen, then this tug of war between gravity and outward radiation pressure is going to become relevant again. It's no longer going to be in a stable equilibrium situation, because once I start running out of my fuel, then I can't really produce as much radiation to hold myself up against gravity. Okay, so again, as I use up the fuel, what's going to happen is I can't really produce as much. If I'm the sun, I can't produce as much radiation pressure to counteract gravity pulling in on me. And so with a decrease of that radiation pressure, now gravity can start to win this tug of war. And so it can contract the core and, you know, start to win the battle between gravity and pressure. And when that happens, as it's contracting, it's going to heat up the core. And so this outer shell that still has a significant amount of hydrogen in it, in this outer region here, now I can start to get fusion reactions taking place there. Instead of just in the core itself, now the shell surrounding the core has become hot enough from that contraction of gravity that I can fuse some hydrogen in the shell surrounding the core. And so when this hydrogen starts to fuse in the shell, the size of the sun is going to increase to become what we call a red giant star. So instead of being 1 radius of the sun, it's now 10 radii of the sun. Okay, and then if we plot that on the HR diagram, now we had spent 10 billion years here on the main sequence, and now we're finally going to leave it again. Okay, and we're going to again head up because our radius is increasing. And because our radius is increasing, we're going to become more luminous because there's more surface area to give off light. However, at the same time, we're moving a little bit towards the right because as we are becoming larger in extent, that means that the layers are cooling off, right? They're not as hot and dense anymore. So the surface temperature decreases even as the size and luminosity increase while we enter this giant region of the HR diagram. And this is really the kind of the beginning of the end for a star like the sun. Okay, so again, as this core shrinks, it heats up and the outer layers will expand and cool. It becomes a red giant, and it's kind of all the stuff I said, only now it's in words instead of on the HR diagram. The luminosity is large because we've got this large surface area, but it's cooler and redder now. In fact, if you could fast forward in time and see what the sun will look like in about 5 billion years, here's the sun today, right? Yellow star, 1 solar radius. Once it gets to be a red giant star, it's going to be this much bigger. So the size ratio here is drawn to scale. And so when it's a red giant star, instead of being 1 solar radius, its diameter across is going to be 1 AU. Yes?
What happens, because the sun is in the middle of the planet,
Mm-hmm.
what happens when it swells up? What happens?
When it gets to like this?
Yeah.
Yeah, so what will happen is that it will engulf Mercury and Venus for sure, and possibly the Earth. We don't know exactly, this is approximately 1 AU, which is our distance, right? So we're going to be really close to the surface of the sun here on Earth. Either it will incinerate the Earth and the Earth will be destroyed, just like Mercury and Venus, or maybe it will be just close enough that it's just a roasting ember, but obviously it won't be hospitable to life at that point. So, make sure you set your alarm for 5 billion years and find a new place to live, because the Earth is not going to be able to sustain you. I say that in jest, but, really it's true. If there is life still on Earth, when this is starting to take place, it's going to quickly become, not really life-sustaining. So if there are intelligent creatures at that point, they're going to have to find somewhere else. I don't know, maybe one of the moons of Jupiter will be nice and balmy at that point, since it will be much closer to the surface of the sun. But again, this is kind of the beginning of the end, so it's kind of just a Band-Aid on the problem. Sorry if that's depressing. Okay, so when you're on that red giant branch, it's still an unstable situation. You've kind of got a temporary source of radiation pressure from that shell burning hydrogen, but eventually you're gonna run out of hydrogen there too. And again, then gravity is going to take over again and contract the core more, and then the core is eventually going to reach an even more mind-boggling temperature where it's hot enough for helium to fuse. Helium is going to require an even hotter temperature of, I I don't know how many zeros that is. 1, 2, 3, 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, okay, or something. I thought it was 10 to the 10 actually, but in any case, it's even hotter than what is required for hydrogen fusion. And when helium fusion takes place, then it's going to convert everything essentially into carbon in the end, right? So it'll go into beryllium, but then the beryllium will fuse with another helium atom, and then you'll end up with carbon. So the ash of this helium fusion is carbon, okay? And for that to take place, you need extremely high temperatures. And so the carbon fusion stage will put, the helium fusion stage will put carbon in the core. And then meanwhile, you've still got helium fusing in the shell and hydrogen fusing in the shell. Basically, you create this onion-like structure where the ash of one type of fusion goes in deeper and deeper. So, when it was hydrogen fusion, then that ash is the helium, and so now you've got a helium shell, and the ash of helium fusion is carbon, and so you've got carbon in the center. Okay? And so for a star like the sun, that's really as far as it's going to go. It's never going to be able to achieve temperatures hot enough to fuse anything beyond carbon. So once it starts to run out of helium to fuse, gravity will try and contract it again, but it will never reach a hot enough temperature to fuse carbon. That's going to require an even more hot temperature. And that could only take place if you had an extremely massive star where that gravitational effect of contraction can be even more extreme. But for the sun, that's not going to happen. Instead, once it runs out of that helium to fuse, it will become even more unstable. The core will contract and it will shed its outer layers of mass. They'll just kind of eject outward relatively gently. The book uses this terminology that was like, what are you talking about? I think it said quiescently or something. Do you know that term? I don't even know that term, but anyway, it takes place relatively gently as the outer layers of the sun just shed. And what's left behind is this degenerate core. The core is no longer fusing things. It ran out of fuel, right? And what was at the core was essentially just the ash of all that fusion, which was carbon. And so this carbon core just got contracted, and basically everything stops whenever the electron forces don't allow it to squeeze any tighter. That's called electron degeneracy. And what's left then is this sort of crusty carbon, hot glowing thing that's not actually fusing anything anymore. We call it a white dwarf star, but it's really not a star. It's more like the skeleton of a star. It's the core that was inside of the star, the ash that was inside, or like a glowing ember left behind after the fire dies. You can think of it that way. So here's some pictures of the outer layers being shed. The terminology for this is a planetary nebula. Don't confuse that with a protoplanetary disk, because they're totally opposite ends of the lifetime of a star, right? Protoplanetary disk is when the star is actually forming, but a planetary nebula is just when it is dying and ejecting those outer layers of its mass. And so there really isn't anything connecting it to planets per se. I think maybe this terminology was made before anybody really understood what it was. But in any case, those outer layers are being shed, and then you see at the center here this glowing white ember, which is carbon essentially. So that is the white dwarf star that's left behind, and the planetary nebula will eventually dissipate, and then you'll only see the white dwarf star. So again, looking at the HR diagram, to synopsize what we just talked about, the sun, or a star like the sun, when it runs out of hydrogen to burn, will start burning hydrogen in its shell and enter this red giant stage in the upper right. Then it will start to run out of hydrogen in that shell, and gravity will start to contract it more, and then it will start to fuse helium. And then eventually, when it runs out of helium, it will eject its outer layers in a planetary nebula, and what's left behind in the core of that is the white dwarf star, and it will land somewhere over here in what I like to call the stellar graveyard. Okay, notice that white dwarf stars are really hot because that's where the core of the star was, but again, they're not fusing anything, and the only reason that they're dim is because they're so small, right? They're just the core of the star instead of being the huge large radius. They're just the core. Over time, these white dwarf stars will simply cool off and move to the right here, and that's because, you know, they're in the darkness and coldness of space, and they're not producing any energy of their own, so eventually they'll just cool off, and at some point they'll become dark, and then they're no longer glowing. At that point, they're called a black dwarf, and they're just basically just like a burnt out skeletal remain of a star. Okay, here's an example of a famous white dwarf star, Sirius B. So Sirius, the star Sirius, is actually a double star, binary star. This one is in the bigger one that you see here is in the end of its lifetime, but Sirius B is already past its prime, right? It's already kind of dead, and all that's left behind is that white dwarf star. So a lot of times when binary stars are formed, they're not necessarily going to die at the same time, right? You can think of it as twins being born. Chances of them dying on the same day are pretty small, right? So even though these binary stars were born at the same time, Sirius B clearly died first, and it's a little white dwarf star left behind where this one is aging and in the process of dying. Whoops. Okay. And so there are a number of white dwarf stars that Hubble has found in globular clusters. It turns out the globular clusters are kind of older. We talked a little bit about the turnoff point in the HR diagram and how you can deduce the age of a cluster. And a lot of times these globular clusters that are in the outer regions of the Milky Way are older in age. And so for that reason, it's common to see white dwarf stars in globular clusters because they're just so old, and so a lot of these stars have passed on, and you kind of see their glowing embers behind. Okay, so in a nutshell, here's the timeline of a star like the Sun. So first, the Sun was born, reaching zero-age main sequence. We're kind of glossing over the formation here, but now it's actually fusing hydrogen into helium, and you know it may have been a little bit unstable here, but it quickly attains stability, and then you know this is kind of just boring, right? It's just going through its lifetime, fusing hydrogen to helium, fusing hydrogen to helium, nothing apparently changing on the outside. Of course the core is changing, the composition of the core is changing, but you don't really see that. It's just continuing to fuse hydrogen to helium, and we're right about here, 4.5-ish billion years in to the Sun's lifetime. Eventually, starting maybe around 7 billion years into its lifetime, so about 2.5, 3 billion years from now, you'll see that the size of the Sun is starting to increase, right, over the next few billion years. And that's going to cause kind of catastrophic climate change on a planet like the Earth. Obviously, this is a different climate change than the climate change that man is producing right now. This climate change actually is due to the Sun. I know some people that are pseudoscientists say the Sun is warming up and climate change isn't real, so it's not happening yet. But, you know, that's not happening yet. That's not going to happen for billions of years. So that's a separate issue. In any case, though, it will eventually take place where the Sun will increase in size and the climate will change on all of the planets, and particularly here on Earth, that could be bad news for life. Once it reaches this red giant phase, it will incinerate Mercury and Venus and possibly the Earth as well, and it will be 1 AU across. Then when it finally runs out of helium to fuse, its outer layers will be shed in a planetary nebula, and what will be left behind is this white dwarf star. Whether or not some of the planets are still there at this point is unclear, but in fact, the first planet outside of our solar system that was ever discovered actually did orbit what we would call a dead star. So it's possible that planets could still be in orbit around the sun at this point. Obviously, their surface temperatures would be much different, and features might be much different than they were before. Like I said, make sure you find another home by then. So I've given you the picture of what happens to a star like the sun. It's interesting that basically how a star will end its life is almost essentially entirely predetermined by how large it is to begin with. A star like the sun will go through this hydrogen shell burning, then helium burning in the core, then it'll have a carbon degenerate shell that will become the white dwarf when it runs out of helium to burn, and it'll shed its layers in a planetary nebula. End of story. But if a star is much, much larger than the sun, its fate will be a little bit different. So here are some other stories of how other stars might be born, right? So these are all protostars entering the main sequence. This one turns out to be only 3% of the mass of the sun. This one is 3 times the mass of the sun. And this kind of pre-main sequence track that they follow is sometimes called the Hayashi track. So it's basically just plotting its progress to the main sequence. And then once it's fusing, once it's on the main sequence, it will start fusing. But whether or not it actually makes the main sequence will depend upon how large. Again, everything depends upon how large it was to begin with. If it's not quite large enough, sometimes we call this a failed star, but really it's a separate object that might glow a little, but it's not really fusing. And so we call it a brown dwarf because it sort of glows, but it's not really fusing of its own accord. And so this is an object that isn't small enough to really be considered a planet like Jupiter, but it's large. It's not large enough to be a star either. It's sort of in this regime in between where it might glow, especially when it's first formed. And so that's called a brown dwarf. That's different from a white dwarf or a black dwarf, right? Because a white dwarf is the end of a star's lifetime. A black dwarf is just a white dwarf that has cooled off. But a brown dwarf is basically something that wasn't quite big enough to be a star. Okay, so another clicker question. Let's see if I can. Okay, that's not in the way, is it? No. Okay. If you don't remember from what we talked about, the HR diagram is shown here, so you might be able to deduce it just by looking at the X and Y axis. And I should say here that when it says temperature, it's talking about surface temperature. All right, we all in? All right, so looks like most of you said B, which is the correct answer. So what's happening, as you can see here, it's going up, and luminosity is on the y-axis. So if it's moving up on the y-axis, that means its luminosity is increasing. And on the x-axis, temperature increases to the left, right? So if it's moving to the right, its temperature is actually decreasing. And the reason I was careful to say surface temperature, so you see here it's marked surface temperature. As I just mentioned, the core is actually getting hotter, which is what allows it to fuse other things. But the surface temperature is actually decreasing. Okay. Whoops. All right, another clicker question. I kind of said the second half of this if you were listening. Okay, let's see how we did. Okay, so most of you are saying B. Interesting. Okay, because the right answer should have been C. Let's see what we're confused by. So once the star ends its hydrogen fusion, the core's size actually decreases because gravity is going to contract in on it. That's what's going to bring its temperature hot enough to fuse something else. So then we've got decreasing size here, which is in turn what creates an increasing temperature here. So C is the correct answer. Is that clear now? Gravity starts to win, contracts the core heats up, allowing it to fuse other things. The rest of the star, though, if it was about the whole star, then you're right, the size of it would increase, right? But the core is actually decreased. Okay. All right. One more. Actually, I shouldn't say one more. I don't actually know. There might be another one after this. Okay, guys, I think feel more confident about this one. Let's see. Answer D. I think that's right. I didn't actually look. Yeah. So, yeah, most of you said this, that it will end as a white dwarf. Yes, so at the end, in between, it will go through a giant phase. That's true. But that's just the beginning of the end. In the very end, it will become a white dwarf. We didn't really talk about pulsars or black holes yet, but as we're going to see, those are what happens to really massive stars. So a star like the sun will never end that way. And red dwarf stars are actually just normal stars that are red. So try to keep all your dwarfs. I know they're not sleepy and dopey and stuff, but try to keep all your dwarfs straight in your mind. So the white dwarf is like the stellar corpse of a star like the sun. A black dwarf is basically what a white dwarf would become after it cools off and is no longer glowing. A brown dwarf is a star that something that wasn't quite big enough to be a star, and a red dwarf is just a very small reddish star. So there are 4 types of dwarfs. Hopefully that's clear. Okay. There was another one. See, I spoke too soon. I should add, maybe this will help. This is something that happens at the end of the lifetime of a star like a sun. All right, we all in? Okay. Looks like most of you said C, which is the correct answer. So, when you have this relatively gentle mass loss, that's what's going to create this planetary nebula. Nova and supernova are more violent things that we haven't really talked about, again, involving more massive stars. And then the dark and emission nebula are more to do with the birth of stars rather than the death of stars. So that's why I was mentioning that this is the end of a star like the sun. Okay, so again, it's sort of a misnomer. It really doesn't have anything to do with planets, but a planetary nebula is the term for this. Okay, and I guess that's all I had for today. Does anybody have questions?